remember the first time I started videotaping, I put like a big old water bottle right in front of me. Oops. The whole thing was like an Escher painting or something. So looking through the water bottle. It's like, sorry guys. So number 4. Okay, true, false. Oh yeah, so if x1, this one here, if x1 less than x2, f decreasing, then f of x1 greater than f of x2. So really all this says is if, and to kind of check this, it's hard to tell what you're allowed to do because you can't get too specific when you're trying to say true or false to some very general statement. But anything that follows this, so if 1 is less than 3, okay, that's true. So if my input for x1 is less than my input for x2, what must be true about my outputs if this is a decreasing function? So let's draw on a decreasing function. The output for my x1, so actually I don't even need to use 1 and 3, I can just use x1 and x2. The output for x1 has to be bigger than. Yeah. So if it's decreasing, they are inversely related. So if my inputs grow, my outputs must shrink.
Yeah, I see. So then it's true.
Yeah, so if they're if it's an increasing function, then of course they do the same thing. As my x's get bigger, my y's will also get bigger. Right? Cool. But it's always, sometimes you guys are too specific. And you give an example that works, but that doesn't tell me it works all the time. Here, it's very general. It just says if I have one input smaller than the other, and then I have a decreasing function, does it really matter what shape that has? No, it just has to be some decreasing function. They all have the same property that they will go down as you move over. There you go. Right? I think it even said strictly decreasing. No, I said decreasing, so well, too bad for them. Yes?
Number 8 on true or false?
Oh, so in general, it's the only number you can't divide by.
0.
And can e to the x ever be that?
No.
There you go. Cool. So you can always divide by e to the x, especially if you're only considering real numbers. So we'll stay with that.
That was the point of that question.
Yeah. Yeah.
Can you get an explanation for number 7 on that true or false? Like, I know the answer, you just can't explain it.
Oh, this comes from, and I can't remember right now, I think at some point I was actually trying to figure out a function that this would be true for. It's really hard, I can't remember if I ever found one or not, I don't know, to come up with something whose inverse is actually equal to the reciprocal, because when they first teach this, students think, that means reciprocate, and I don't blame them, because that's what the hell it means. I wish we didn't use that symbol for inverse, but we do. So, oh well, too bad for us. But that's the mistake. It doesn't equal that in general. Does it equal that for some function? Maybe, I don't know. But it would be a very specific function.
Because the way I was looking at it, it's like inverse sine or inverse cosine or inverse tangent. It's that kind of deal where it's just one over cosine or inverse sine. That's the way I was looking at it.
Oh, no, you got to be careful. No. Inverse sine is not equal to 1 over sine. No. Inverse sine is its own, it's arc sine, if you want to call it that. And the reason they came up with arc was because of the whole -1 crap. They said, let's just get away from that and call it arc. Have you guys heard arc sine? Yeah. Okay, good. Sometimes teachers don't even say arc sine. But it just really means the same thing as this. It just gets away from the confusion about this not being just the reciprocal. This really does mean the opposite function. So sine normally has angles as input. Arc sine or inverse sine has angles as output. So the arc sine or inverse sine of 1/2 would be, 30 degrees or pi over 6. Is that cool? And you had to be careful about their domains. Remember that whole thing?
Yeah.
I mean, in general, is sine invertible? Is sine 1 to 1?
No.
No, because it doesn't pass horizontal line test. But if I cut this part off, and then cut that part off.
Yeah.
Now it does pass horizontal line test, and that's why the inverse sines domain is what it is, because it's got to be that for there to be, or range in this case, and it's got to be that for that to even exist. And that's where the whole freaking, remember solving for triangles, and you had a situation where it could be two different triangles, if you swing the other leg in. Does that sound familiar at all? This is pre-calc, so it's been forever since you had pre-calc, maybe not, but because of the ambiguity in the output of this inverse sine. It's just a reference angle, and you might be in the other freaking quadrant. That's why you had two possibilities. Some of you guys have no idea what I'm talking about. He's just standing in front of the room doing this. Okay. Anything else from the homework? Okay. I'm an optimistic fool, so I'll take that to mean it's going well. So last time we officially got into 2.2 a little bit. I had a few people ask me a few questions about section 2.1 in my office, but I'm not seeing any questions. If you really understand 2.1's point, that you can look at every problem they give you as, let me just figure out the 2 points for this situation and find the slope. Let me just figure out the 2 points for this situation and find the slope. You're fine. That's all it really is. So if there's no questions on 2.1, I'm just going to get right back into 2.2. Okay. So last time, I think the last thing we looked at, let me do a problem sort of like that. Oh, let me see if they have one in here. Here we go. Yeah, let's do that one. Why not? Now, I want you to first create a table of values. And what kind of inputs should you use to investigate this?
And it's very close to 0.
So like,
0. Oh, no.
why can't you use 0?
Because
So maybe I can use
negative.
0.5. Now, yeah, exactly. So you bring up a good point, but let's see, 0.5, 0.1, 0.01. And I'll see if that's good enough. If it's not, I might have to go to 0.001, who knows. But I also want to investigate negative 0.5, negative 0.1, negative 0.01, and see if they're approaching something. So finish that table out for me. So of course, when you're using your calculator, you've got to be careful about it. You're going to have parentheses here. You're going to have parentheses there. If you have one of the newer calculators, it actually extends the square root sign. You guys know that? So if you have I didn't bring any spare calculators, so if you don't have a calculator, just hang out. There's your favorite wall. If you haven't picked a favorite wall, you should.
How many decimal places? Just 2?
Yeah, it depends on the size of the thing. So if it's like, what are you getting? What kind of number?
Like for 0.5, I got 0.24.
Okay, yeah, so that's fine. In general, I might want to go a few more, but it all depends on how easy it is to see the pattern. Maybe you need a syllabus, by the way, that. Oh, I do have one more. you guys some things here.
There we go.
Here, let me show you the ultimate help on this kind of problem. So let me let that warm up. Are you guys, where the hell did I put my pen? Oh, there it is. What are you guys getting here?
0.243,
243?
0.248,
0.250.
0.251. Oh wait, hang on.
They got 0.250.
250, yeah, I got to put for that one, and then
Do they just repeat, right?
yeah, and then
And then 0.252.
252?
Yeah. And then 0.258.
258? And if you just went in and tried 0.001, I don't know if anybody did, more than likely it says 0.250 and something, right? So you feel pretty good saying that this looks like the limit is what?
0.25.
Yeah, 0.25, a quarter. Again, this is analogous to finding like I said earlier, finding the solution of a system of equations by graphing. It's dependent on how nice the function is, just like it's dependent on how nice these functions are. But that looks pretty good, but it could be 0.2503. I don't know. I can't tell. I don't have good enough resolution, but I want to show you something real quick, and then we'll do this the algebraic way.
Professor. So with regards to this, like the table and everything like that, when you're finding what you think you're like the slope is, I guess at this at that point, you're
saying it. I'm sorry.
The slope, right? You're just finding that the limit. Then is that what you're calling it?
No.
Or?
So this is I'm not doing a slope because I haven't picked like 2 points to do.
Okay.
I'm not stepping in. The idea of stepping in close to something, the limit, it could be applied by itself in a lot of different situations. So one way it could be applied is to let one point get really close to another point. Here I'm only dealing with inputs, not points.
Okay.
So I'm not finding a slope. I actually am just finding values.
I see. Okay.
And I never can plug a 0 in because it's a problem spot. So instead I just get really close.
Okay.
Okay, is that cool? Okay. So watch this. I don't know. Here's one of the really cool things about the table function. So if you input the function here, square root. So if you have an older calculator, it doesn't extend the square root sign. You have one of the new ones, it does. And I definitely like that. So divided by x. If you go to table, normally it has it predefined and all this kind of crap. Oh, neato. What the hell is that? That's new. Ooh, neato. Okay, sorry. Yeah, that's like triple geeky there. Like, neato. If you go to window, it'll show you all this crap. If you go to table set, right above window. And I don't know if any of you guys have ever used anything here. Let me show you where it's big. Here. If you tell it, I want the independent variable, ask, instead of auto. When you go to your table now, it's going to be blank, and you're going to be like, thanks, Jeff. But if you put in there 0.5, bam. 0.1, bam, and so forth. So it's a nice, quick way just to get specifically what you want. Is that cool?
Yeah.
That's pretty damn useful, right? Okay. All right, so that's what I want to show you. Now, of course, you can always do this too. On any limit problem, if you graph this thing, of course, my window's all freaky. Oh, what scale I'm on there? Let's see. Nice. That's so much better. So if you do, let's see what zoom fit. Oh my God, I got crazy options here. Okay. Zoom fit sometimes works, sometimes doesn't. It tries to show you interesting aspects of the thing. Let's see what Zoom fit does to this. If you need it. So if you try to put in there second calc value, so you can do that for like x equal to 0.01. It'll tell you what it is. But if you try to do second calc value for 0, y will just equal the void. You know, it's like it doesn't know. But I mean, it's if you trace it and stuff, you can kind of see where it's going. Where the hell trace? Oh, I'm right on there. You know, so you can see it's approaching 0.25, sort of. The resolution isn't all that great, but you know, that's another way to kind of do it real quick. If you want to see what it looks like it's going to be. Okay. So again, I'm kind of assuming you guys have used some kind of graphing calculator, possibly to some degree. And if you haven't, you can always just let me know, and I can show you a little bit more on there. But that table thing is really, really useful for a lot of functions. Now, how can I do this algebraically? Of course, all that, if you're home watching this, you didn't see any of that. If anybody ever notices that I need a reminder to turn that around, just tell me. I'm doing something up there and I forgot. I always hate when I do that. How do I do this algebraically?
Multiply by the constant.
Yeah, exactly. So, root x plus 4 minus 2, I'm going to multiply by...
Plus 2.
Yeah. Alright, so take a second and finish that out. X goes to the void. Sounds relatively quick. Yeah, you'll get x goes to 0. You get x plus 4 minus 4. So you get x over x times this stuff. So the x cancels. So that's why you never multiply through on these problems. Because you're always... See, from the very beginning, what happens when I plug a 0 in? I get 0 over 0, which is actually, like I said earlier, a good sign. That means that the problem might be the same on the top and bottom. It might cancel, leaving you with something you can actually use. Now, algebraically, the only time I can actually cancel these is as long as what is true. I can only cancel x over x and say it's 1.
There is no addition or subtraction.
Well, I mean, don't get on that level. Everything's cool. I can kill them. But I always have to assume that x, in this case, x is not 0. Right? X can't be 0. Or else, you know... And what's really cool about the limit?
It's approaching 0 or not.
It never gets to 0. So I'm allowed to do this because this guy is telling me it's never 0, dude. I'm like, oh good, the only time I can't do this is when it's 0, so I can kill it. You guys are kind of with this? There's a whole theorem that they set up to make it all sound big and bad, but it's just, I can kill it except when it's 0. It's never 0, so I can kill it. Yeah.
So if the limit was like -1, we wouldn't be able to cancel it out?
No, if the limit was -1, and I see what you mean, because then x could be 0, right?
Yeah.
But what's the whole idea of the limit?
Approaching it.
Approaching this, so getting really, really close to this. And 0 is not close to -1, believe it or not, because -0.9, no, that's close to -1, right? You guys with me? A little bit there. Okay. So then, if I plug a 0 in, I get 1 over 2 plus 2, I get 1/4, which is the 0.25 we thought. Really cool. I like it. Okay, so just like with solving system equations, we have a graphical kind of table or graphical method to do it, which isn't always perfect. And then we have an algebraic way, which will always give me the right answer if I can actually do it.
Wait,
Right.
if you get to the 1 over 4 from the x plus 4 plus 2.
Oh, so plug a 0 in.
Oh, okay.
So for limits, that's the first thing I do is I plug it in. I only do other stuff if I can't plug it in, if it comes out to be something indeterminate. So I'll tell you right now, here is a trick question that will be on the test. Somebody in here right now will still get it wrong, which is okay. I mean, it's, so I like to do something like this. What you got, Jeff? I don't know what you got. And then I'll have somebody attack it. They do the conjugate. They do all this mess. They get the completely freaky ass thing going on.
So unless you get 0 over 0, you can directly plug in.
Exactly. So the only time I'm not allowed to just plug this bad boy in is if I get something that's not determinate. This means I don't know what the answer is. So then I try to change the form of the question so I can see what the answer is. Here, I know what the answer is. What are you going to plug a 4 in? And why do I have a t there? I was trying to mix it up, and then I forgot to mix it all in.
Wasn't going to work.
Yeah, I know. It's like, well, Jeff. All right. So what are you going to plug a 4 in now? You get 0 over 2, which is 0. Or if I would have had it the other way around, just so you know that it's not just because it's 0. If I would have had it like this, the answer would be
Undetermined.
it's not indeterminate. The only thing that's indeterminate is, well, not the only thing, I'll be careful, but one form that's indeterminate, we will learn more, is 0 over 0. Yeah, it's infinity. Positive infinity, to be more specific. Because it's positive, right? It's going to be 2 over 0. It never gets to 2 over 0 because 2 over 0 itself is just undefined. But specifically, this just grows without bound as you get really close to 4. Because think about it, when you get really, really close to 4, you're dividing by 0.1, 0.01, 0.001. It's getting freaking big, right? So, they'll say that this is does not exist officially, but I at least think of it as a more precise answer than does not exist. Is it infinity or negative infinity? Right? They're both does not exist. Because a limit means, what's the ceiling? Well, you go to infinity. So there's no freaking ceiling, but you can be more specific. Did you go through the ceiling or did you go through the floor? Right? Okay.
So when we're, like you said, that would end up being undefined. We just need to identify between positive or negative infinity.
Does not exist. Be careful. There's actually a weird little difference. Yeah, does not exist. But I will accept it if you just put infinity. That actually implies it does not exist. It's just being a little more specific about the answer. Yeah. So I need to see the infinity or the negative infinity. So if I would have turned this around, well, I guess I got to be a little more careful there. Let's get into this.
I have a question.
Yeah.
So as the limit of t close to 4, we can actually plug 4. Because did you say earlier that, for example, limit x close to 0, we cannot plug 0?
We did. But we noticed we got this.
Okay.
That's what told me to keep going. Here I get something I can actually determine.
Right.
Yeah. So to be fully, screw it. I made a mistake. Let me show you this here. Let's see if I really. Yeah, that's fine. Yeah, I guess they did make things too much. So if I put here limit, now tell me why I might have to do this for this problem. Limit as t goes to 0. If I put a little plus sign, just think about it. If I have a function and it's doing some weird stuff, and I want to know what the limit is at that point, I can approach it. We've done this in the table. We did it from above. We did it from below. We see where they're going. So that means I would go from above. That's what this plus sign means. I'm going to 0 from above. And then I can go to 0 from below. And see if they meet. That's exactly what we do when we make a table of values to investigate a limit. Sometimes I'll have a function, and the fact that the function itself is in there, why in that case do I have to have the plus sign up there? Because, of course, I don't want to go into complex numbers. This is all basically known to be over the real numbers. So I have to put a plus sign in there because I can't plug something in from below 0. Cool? But in general, for the limit as x goes to a of f of x to exist, sounds very formal. The limit as x goes to a from above must equal the limit as x goes to a from below, and they must equal the same thing, some L. They must both exist and they must both agree.
So like 1/4 or...
Yeah, so exactly. We saw them both going to 0.25. Now, if we would have done it from both directions, and one said 0.24, 0.25, and the other said 18 point... No, they don't agree. So visually, what does that look like?
A break in the graph.
Yeah, a break in the graph. So, actually, I'll tell you what. This is a better way to do it. Put this up here. Yeah, here we go. This is good. I need about 4 minutes here. All right.
What's L?
L is just the value. It's sort of like the equivalent of x and y. It's just a certain number. So it's trying to say it's not infinity. It's defined. It exists, and they agree. So they both have to approach the same thing from both sides. If they don't agree, what's the limit as x goes to whatever? I don't know. They don't agree. So I can't say that there is a limit. So, let me see. Let's look at this. Problem number 7. Let me freeze that. Whoops, okay. My finger's going to stay there. Alright, can you all see that? Okay. So let's take a look at this. This is the very first thing. Let's go grab the door. It's not going to help out that much because it's got a vent in it, but we'll see what happens. What is that very first question they asked? 7a. What's happening there?
What are the functions on the left side? Coming from the left to 0.
Okay, good. All right, so you can think left and right. I always have trouble left and right, so I always think from below or above. So I'm approaching 0 from below, and this is the graph of g. Obviously, g is what kind of function?
Piecewise.
Piecewise. I love it. It's defined in pieces, so it's a piecewise function. It's crazy. So as I'm approaching 0 from below, now I notice people have trouble with this. They're not sure how to look at the graph for this question, but the whole thing is, as my inputs approach 0, what are my outputs doing?
Approaching -1. Decreasing.
They're approaching -1. How we doing? Is that all right? Let me zoom in a little bit. And all right, Jeff, stop doing that. Okay. So as I approach 0 from below, as my inputs approach 0, my outputs approach -1. Yes, sir.
You want to move the camera?
Oh, yeah, thank you. Perfect. Focus. Okay. Focus again. Okay. Now watch this. As my inputs approach 0 from above, is that the next question? Good. That's a good idea. As my inputs approach 0 from above, What is my outputs doing?
-2.
Are you concerned at all with the fact that there's an open circle there?
No.
Why not?
Because
It's approaching that, it's not there.
It's an asymptote.
It only approaches it. It doesn't go.
I love it. The limit doesn't give a shit what's actually happening there. It just says, what does it look like it's doing? Where's it going? Not does it get there. So the function does not have to be defined there for the limit to exist. Now notice, part A and part B are very specific limits. Part A is the limit from below. Part B is the limit from above. Now those two answers were -1 and -2. So what's the answer to part C?
Doesn't exist.
Doesn't it? They don't agree. There's not a single limit at that point because there's not a single possible output that they would agree on. Now be careful. The answer is not -1. It's not asking you what f of 0 is. It's asking you what is the limit, and the two limits don't agree. So there is no limit. It's not defined. There's no limit.
So wait, what is so for the limit of 7a there is what is it again then?
-1.
Okay.
And B was -2. So as my inputs approach 0 from below, my outputs approach -1. As I put inputs going towards 0 from above, my outputs are going towards -2.
Okay, so that's just we haven't done anything with it yet. Then.
Say again?
That's just those are just other ones. We haven't done anything with it then at that point, right?
Yeah, there's nothing else to do with them. They're just what the limit is.
Okay.
What does it look like it's going towards?
Okay.
So A, B feed into C. So I know C is no good because A and B don't match. That's exactly what that theorem says. What about part D? Limit as I go to 2 from below. So my inputs are going to 2. My outputs are approaching 2. I love it. Doesn't matter that there's a hole there. From above, 0. And what's the limit as t goes to 2 then? I love it. Doesn't exist. I don't care that the function... What's f of 2? F of 2 is 1. I love it. That has nothing to do with it because it's like an asymptote there. It's like I never get there. I just care about what it looks like I'm doing. So the function can do whatever it wants to there. Yeah.
So like for E, where it says limit g of t, t is going to 2 positive.
Yeah.
Would it be 2 as well?
Well, so limit is the inputs approach 2 from above. What are my outputs doing?
Decreasing. Or decreasing.
Going towards 0.
Yeah. So it's 0.
It's 0.
Okay.
Exactly. From below it's 2. From above it's 0. And you can pretty much do exactly that. You just follow, as my inputs do this, my outputs go there.
Okay.
Yep. And G, I think I already asked you guys, G of 2 is 1. What's H?
3.
H is beautiful, right? What's nice about here? There's no problems with it, right? I'm going to get a little ahead of myself right now, but the big difference between all of this where the line just is carefree and then this weird shit where it does really weird things is this is what's called continuous, and this is what's called, incredibly enough, discontinuous. I would like uncontinuous. So discontinuous things are where either the limit does not agree or the limits agree but the function is not defined there. So anywhere that I have to pick my pencil up to keep going. So if I have a point like this here, that is a place where it's discontinuous. The limits agree, don't they? The limits are fine. They both go towards that same open circle, but it's discontinuous. It jumps over that point.
But the function on this particular point is undefined.
The function's undefined, exactly.
Undefined on this
It could be, maybe it's there. And this is, we'll say this is B. So what's the limit? Just to give you a lot of letters up here. What's the limit as x goes to A period of f of x? B, 11. It looks like it's going to be. What happened? Oh, yeah. I'm sorry. So this would be B, 11. But f of A is whatever. F of A. Let me call that C, whatever. Is that cool? So the limit exists. The limit exists because the limit does not care what is actually happening at that point. The weirdest thing possible can happen, then the limit wouldn't care. It just cares that they both look like they're going the same way.
So the limit is there, it's just discontinuous?
I love it. The limit's there, but it's just discontinuous. So to be continuous is more rigorous. There's more requirements. Not only does your limit have to agree, but you actually have to go there. Right? So that hole has to be filled in for it to be continuous. You guys semi with me? And the word continuous, it should mean I could just go flow right through it. Just I don't have to pick up my pen. But to get there, I had to pick up my pen, make a circle. That's not continuous.
That was for F, right? F's is continuous? Just making sure.
Oh, yeah, F was sort of like that same situation in a different way. There I want to make one that connected. Here's one that didn't connect at all. Yeah.
So if it's piecewise, then that means it is still no answer for F.
Oh yeah, definitely there's no answer for it. It's not defined. The limit's not defined because they don't agree. The two limits, they don't agree. Cool. It doesn't matter that it actually gets somewhere. It's actually defined. The limits don't agree.
Right.
Cool.
I'm still a little like confused with H, just because it's like.
So with H, again, we're only talking about limits.
Right.
So I'm not even. I brought the continuity in because if something is continuous, then obviously the limits exist there. Because continuity is harder than just the limit existing. Because to get the limits to exist, they just have to both look like they're going the same place. They don't actually have to get there. To be continuous, you actually have to get there too. So through 4, where am I at here? It's continuous. It doesn't have any jumps. It doesn't have an open circle. So that means it's actually the limit exists everywhere there.
Okay.
But if you want to look at it the other way, as I approach 4 from above and below, it looks like it's going in the same place. Therefore, that limit exists, and it is 3, because that's where they agree. So I could have put an open circle right there. Would that change my answer to that? No. I love it, because the limit doesn't care what actually happens there. They just have to look like they're going to the same place. How are we doing? Now, trust me. I want you to really understand. We're investigating the hell out of limits, because they are going to be what builds the foundation of calculus. So we have to really understand a limit by itself doesn't care what's happening at the point. So it actually opens up our ability to do all this weird shit, like I was talking about earlier. I want a slope at a point, but algebra says you must have 2 frickin' points to calculate a slope, right? So therefore we have the idea of the limit, which says you always have 2 points. You never have the 2 points right on top of each other, do you? But in the limit that they do go right on top of each other, then I can say what's the slope right at that point. You guys, so the limit is what allows me to help calculus figure out the slope at each point. Because algebra is saying, you need 2 points, what the freak are you doing? Calculus is like, you always have 2 points, don't worry, man. There's this limit thing. It's exactly the conversation that happens between the two subjects. Okay, how are we feeling? I mean, this is all probably brand new ideas. So it will take a little while to sink in. I'm hoping some of you guys realize it isn't that it's difficult. Once you understand it, because like you know that there's some math that once you understand it, the problems are still hard. You're like, oh shit. This is something where once you understand it, it's easy as hell. But it's new, so it's going to take a little while to sink into your brain. Oh, let's see. Okay, let me make sure I don't skip over anything. Oh, on page 92, there's a little theorem 3. It's in that little box. Yes, sir.
Can you have a continuous function that doesn't have a limit at a point?
So a function that's continuous through a point?
Yeah, if you have a continuous function, is there ever a point where the limit won't exist?
So you got to be careful. When you say, if I have a continuous function, I'm guessing you mean it's continuous everywhere.
Yeah.
Okay. And then you're asking me...
But by definition, because it has to have a limit. To be continuous, it has to have a limit at every point.
More than that. It's got to have a limit exist, and the f function has to actually be that value. Therefore, you said, is there a continuous function where you
Have a point that has no limit.
Yeah.
Then it wouldn't be continuous, right?
exactly? I mean, the closest you can think of, and as quickly that you see that it's not continuous, is where you have like an asymptote where it does that or something. So these two don't agree, but it's discontinuous because you actually have to come up here and start over again.
So as long as the function is continuous, if you have a question, find the limit. As long as it's continuous, there is going to be a limit.
Exactly. If it's continuous through a point, the limit must exist at that point. Because to be continuous, the limits have to agree.
Right.
And then it's just that extra condition, oh, they actually have to go there too. So the limits don't care if you actually get there. Continuity says, well, you better freaking get there too. So you know, it's not this big canyon you have to jump over. Now I'm thinking about Evil Dead where the whole bridge collapses.
So if we
Put the bridge back up and let Ash get back home.
so every function has a limit, we can study a limit for every function.
Do it again.
Continuous or discontinuous function has a limit. We can study the limit for both.
Oh, sure, yeah.
But the only thing is, with discontinuous, the limits won't meet a point that the f would be defined.
So let me show you something. So the one I just put up here, if I had a function that was cool everywhere except right there, so technically it's a discontinuous function. It's only discontinuous at one point, so it's a little unfair for the poor dude. Everywhere else he's fine. But technically it's discontinuous somewhere on its domain, right? But the limit, is there anywhere the limit does not exist? No, the limit exists everywhere. Because again, that's the only possible place where there'd be a problem, and it's not a problem because both sides agree. So it's the fact that continuity is a more difficult thing to achieve. This is not continuous, but the limits are cool with it because it's not as hard to achieve that. Continuity, you got to fill that hole in. You got to put the bridge back up, right? Okay. Oh, this is that theorem from earlier. This just says the limit at a point only exists if and only if from below and above agree. I just wrote it in kind of a different way. Anybody ever heard that phrase, if and only if?
Yeah.
And what does it mean? IFF, I like that. IFF is the shortcut.
Conditional, like under certain circumstance or condition.
So if you know any logic, not only does it go this way, it goes that way too. So if that's true, and if that's true, that's true. It goes both ways. So if and only if is like an arrow pointing in both directions. Right? Normally if would only go one way. If I forgot my umbrella, then it rains. Right? So it only if I forget my umbrella, then it's going to rain. But it was if and only if, then I can forget my umbrella and it rains, or if it rains, it makes me forget my umbrella. It would work both ways. That's enough logic.
It's like the vertical line test. A function is only a function when it passes the vertical line. Right?
And if it passes a vertical line test, then it's a function, sort of. Yeah.
So just to clarify, it doesn't have to be both of them for that. It can be one separate.
Say again?
As long as like limit like with the x with the 8 into the negative power equals to the one on the left, the one on the right can equal the same thing, right? Doesn't mean that they both have to be that to be that, right?
I'm not sure if you got your question. So the only way that you can say a limit exists at a point is if the limit exists from both directions.
Right.
And they agree. Good.
Where else would a limit exist if it's not a point?
No, I mean, I put an emphasis in the wrong place, you're right.
Oh, okay.
Yeah, we only talk about limits at a point at this moment.
So don't do that.
For us, we're going to stick with just that, limits at a point. Is that cool? So I'm not sure what your question was, I'm sorry.
You answered it.
Sweet. Okay. All right. I just want to make sure I don't miss anything. Nah, we'll get back to that. Then we get into infinite limits, which I sort of talked about a little bit, and this is not a big deal. I mean, once you come out of pre-calculus, your life for a while is dominated by vertical asymptotes and horizontal asymptotes. So, infinite limits, actually, they're kind of hiding something. It either means that the output is infinite in a way, and we talked about that earlier, or it means that the limit is going to infinity. So the limit is x goes to infinity. Do they do that somewhere? Not yet. Okay, that's coming. blah, 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 blah. So, let's look at something here. Let's look at this one. This is coming back to the earlier example. So there is a difference between these two, not just because one has a negative, someone has a positive. That is it, but they don't have the same answer. And what's the fundamental? Now, both of them are somehow related to what? Because what do you get when you plug a 3 in? First thing you do. What do you get?
Infinity.
Some kind of infinity. Now, I said it that way specifically. It's some kind of infinity. Now, here, what kind of values are coming out of this? Because I'm going to 3 from above. So what are you putting in there? A little bit higher than 3, right? So you put 4 in there, 3.5, 3.1. When you subtract 3, it's still positive. So it'll be positive divided by positive is positive infinity, right? What's happening over here? What kind of numbers are you plugging in? You're going to 3 from below. So you're putting 2 minus 3 is negative 1. 2.9 minus 3 is negative 0.1. So you're going to get positive divided by negative. So this is going to negative infinity. Cool. So it's going to be that situation where I have at 3, I have this asymptote, and it's going to look something like, well, which way? This way. This is where it's going to infinity from, yeah, I'm doing it right. From below, it's going to negative infinity, and from above, it's going to positive infinity. And of course, there's a horizontal asymptote at 2, and who gives a shit? All I care about right now is that. What would your horizontal asymptote be? That would be this. Limit as x goes to infinity of 2x over x minus 3. What's the answer to that? What happens when x is really big? I told you this is your pre-calc 3 situation shortcut. What situation are we in?
1.
All coefficients.
Yeah, the degrees are the same, so it's the ratio of the coefficients, so 2 to 1. So it'd be 2. So I have to have a horizontal asymptote of 2 there. If you want to be all, or a little more precise. I would not call that graph precise in any way.
That's correct.
You guys with me? So that's, I could have them agree. They could both go to infinity, but the limit still doesn't exist because it's not contained. They just agree on infinity. Here, the limit as x goes to 3, what would that answer be? Just the limit as x goes to 3, what would that answer be? I like 6. I like that. Again, not undefined, but does not exist. That's the one time that it's just that. It's not even infinity. It's that there's infinities they don't agree on. Oh, that's like really bad. At least if you want to agree, oh yeah, we're going to infinity. We don't exist in that direction. But this is like, I can't agree which direction it goes. You guys follow this? The one time I would say that answer just specifically does not exist. Because the two limits don't agree. I love it. All right. Okay. Okay. The last little thing, and then we'll head out of here. I'll make up for yesterday when we left like a minute and a half early. Yeah. Okay. Now, some of this should actually be, and we sort of already done some of this, to be honest with you. When I said the limit as x goes to 4, square root of x minus 4, what am I doing? It doesn't matter. Whatever. Blah, 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 whatever. What do we do there?
No, it just it solves itself, right? If you plug the 4 in.
Oh yeah, if you plug the 4, I like that it solves itself. Go. No. If you plug a 4 in, but we sort of did this rule. Look at this now. To me, when I first learned this as a student, it's kind of like, duh. But you do have to explain, and you have to be really careful. This isn't like the limit is distributive or something like that. What this really says is it's making it very clear what situations you can just plug that across everywhere. Because it is actually a little weird. There are, for example, if I have 2 here, can I just pull a 2 inside? Does somebody know how to actually write that? Yes, square root of 4x. So there's very defined ways to move things inside, outside. So the radical is not linear. You can't just distribute something inside. You actually have to change it. Here, this is defining the situation where it looks like the limit can just kind of distribute or something. But I always thought, I'm just plugging the damn value into my whole function. So you're basically allowed to do it almost everywhere. Right? So we can add 2 things together. So if I had the limit as x goes to 0 of 1 over x plus, what you got, Jeff? 2 to the x. What's this part? 1. I love it. But what's this part? Yes. In fact, it would be undefined because it would matter which direction I'm coming from, wouldn't it? Coming from below or above. So this would just be does not exist. But I can just go ahead and plug that into both parts. It's kind of like you kind of like, it's like, well, duh, of course you can in a way, but you have to really spell it out that the limit is allowed to do that kind of thing. So it's allowed to go across addition, subtraction, what's called scalar multiplication. Just multiply by a number, product of 2 functions, and then incredibly enough to division, but of course, as long as the bottom's not 0.
Professor, did you want that on the video?
Sort of. It's just in the book. You're okay. Okay. How do you guys feel on that? Those properties, to me, I never looked at like 3 plus x as 2 separate functions. That is a single function. You with me? So to me, these properties, most of them didn't even need to be stated. Now something like this in general, whenever you multiply things get a little weird, but this is still a single function. F times g defines a new function. So if I want to evaluate it today, I just plug the freaking a in. So I always think that they make a little too big of a deal on some of these things. So this section is really where you start to apply the algebraic method of doing these things. So for example, where am I at here? But this is about the roots, right? You can plug it into a root function. Blah, blah, blah. So for example, here. Well, this is not even interesting. You just plug a -2 in, and then you get down to there, right? So I'm not going to be overly critical of this. Here we go, finally. So this is exactly that problem we did earlier. Multiply by the conjugate, go through it, and then plug the 0 in. And this is where they apply it can go inside the radical, that rule. You with me? So some of the questions in the homework is going to ask you to write the rule as you do the work. Do a few of those. I mean, don't worry too much about it, because those rules should be, they almost shouldn't exist, because when you multiply 2 functions, you get another function. You just plug the value in. It's not that big of a deal, but this is important, being able to do the algebra on some of these problems. Let me see if there's an example. Oh, okay. Let's talk about this one, and then we'll, you just got to love the name of this theorem.
Squeeze theorem.
Squeeze theorem. This is the last section we're doing, by the way, section 2.3. And I don't want to make a huge deal out of this, because actually it's very specific situations where this really applies. But it's good to know that it's out there and exists. The idea is, if I had a function, some function f of x, and let me see, which way did they set it up? Okay, I just want to make it the same as the book. It's always smaller than g and h, or at least possibly equal to them both in some cases, right? So basically what it says, if I have a function that's always in between 2 other functions, so here's my f function, here's my h function, and then here's my g function. Here's f, h, no Jeff. Here's f, h, and then here's g. You can see why it's called the squeeze function. So at this point A, Yes, sir.
So are F and H actually touching, or is there a space between them that allows G to pass?
That's the neat question. It's not, and these aren't physical things. They're just functions. Functions can cross. They're not going to like have a collision, right? So it doesn't need a channel to make it through. They actually do touch at that point. That's the whole idea. And this is where that touching comes in. And they can touch a lot of times because it's allowed to equal anywhere they want to. You with me? But I didn't want to do that all. It could touch anywhere else it wants to. But it's all this dude in the middle, this noodle in the middle, is always in the middle. That's the point. So if there's a point, if at A they touch, and the limit of F at A is L, that is a phrase. The limit of F at A is L, and the limit of H at A is L. Then what's the only thing common sense tells you about G? It's got to also be L, because if it wasn't L, it'd be a little more. Well, then it's higher than this dude. It's not allowed to do that ever. If it's a little below L, it's less than that guy. It's not allowed to do that ever. It's always got to be in between. So if they do both touch, like Sawyer said, it's actually perfect. It doesn't leave the guy any room to go through, so he must agree with both of the other functions. It's almost too easy of an idea. This is one place where the concept is easy and the problem looks disgusting as hell. So let's do one problem, and then we'll go ahead and take our field trip. We'll leave nice and early so I can make up for the debacle from last time. Let's see. Where's a good example? Am I in the same place? No, my book flipped back. Let's see. There we go. And there is a sparsity of questions using the squeeze theorem, so it's not a big deal, but I just want to show you how it works. Because the math involved is actually kind of interesting. There's just no way for me to do that nicely, so that's too bad. Number 35 is what I'm trying to look at. So I want to show that the limit as x goes to 0 of x squared cosine 20 pi x equals 0. Now, oh, really? You jackass. Alright, don't read anymore. The other problem that's for homework doesn't give you any clues. This one gives you some clues, which they shouldn't. They don't need to. This is the function I'm trying to say something about. So which one of these do you think that function that I've got that I'm looking at is? G. I think it's G. So if I can develop a function that's always less than or equal to that, and a function that's always greater or equal to that, and they agree at 0, then it's going to squeeze that to be the same value. Now, these kind of, like I told you, these problems are a little contrived. It does happen in the real world, but just not a lot. You almost always have to have a trig function here. Because trig functions are, I love it, limited range, or bounded, right? Bounded above, bounded below. So you need some kind of bounded function, because what's true about cosine of who gives a shit? Sorry. I just hate that they load the inside of that stuff down, and that always throws people off. Sorry. But it's cosine of who cares, right? The amplitude's not changed yet, and that's kind of like an amplitude if you want to think about it. But what's true about that function? What's the bounds on it?
Pi over 2 and negative pi?
I don't know. The outputs of this guy.
Oh.
What's the most it could be?
1.
Yeah, it's less than or equal to 1, and it's greater than or equal to negative 1. Now, is that the G that I want? Is that the function I want?
No. Yeah. It is. Yeah,
You sure? What's my function I'm talking about? Talking about that function. Do I have everything I need in there yet?
No.
But I focus my attention on the part of the function I'm working with that is actually bounded. Is x squared bounded? No, so it better not be in there. I want to focus on the part that's bounded, and I can write it in that form. It's bounded. So now it looks more like that. Yeah, I'm pointing to it. Neat. What am I missing? So then I multiply everything by x squared. Now look at the rest. Yeah. That's where these came from. Right? And they're actually telling you to do it on the calculator, but screw them, you don't need to do all that. You guys with me? So you build your function that you want based off of, what's bounded, and then you build the function off of that. So what's the limit as x goes to 0 of this? And here's the bad part, just writing everything. All right, what's the limit as this goes to 0 of negative x squared?
0.
It's crazy. And then the limit that we are interested in, blah, blah, blah. Limit as x goes to 0 x squared. Therefore, the limit of x goes to 0 this must be 0. Done. Squeeze them. It's a really cool theorem, but there's not a lot of problems because it just doesn't happen a lot. It's almost a very contrived thing. But real quick, if you graph that thing.
So is that just a proof and not...
Yeah, that's a proof.
Okay.
And actually, it's called a construction proof because we sort of constructed what we wanted as we went along. We want that, we constructed it based off of something else. Last little thing here. No, this is still that same problem. Just so you know, I'm not lying to you. How do you guys, anybody play music, play guitar, something? Play guitar? And you've obviously, have you ever worked with equipment that shows you the waves and stuff? Yeah, okay. And of course, if you pluck it and you watch it, if you don't do anything else, over time it's going to dampen down, of course, because there's resistance, right? So if we look at this function, x squared cosine 25x. And my window, I don't know, let's see what this looks like. Zoom 6. Yeehaw. Yeah. Yeehaw. All right, let me change my window a little bit. Let's make this. All right, that's better. So that's exactly the kind of thing you might see as you let, of course this goes in both directions, which is like time going in both directions. But that would be more like you pluck a string on your guitar and it oscillates, and of course over time it dies down. Thank God, or else all the guitars in the world would still be playing. Whatever. Like, hey, how you doing? But watch this. If you put in there x squared, and you put in there, no, Jeff, put in there x squared. No. You put in there x squared, okay, and you put in there negative x squared. You can pretty much see it in the graph that was there. You can pretty much see them. So there's a ceiling and the floor. There's your f, g, and h functions, right? So my noodle was just a very specific example. Here I got G just bouncing from ceiling to floor, but it's always contained in the middle. A beautiful example of squeeze theorem, right? It's really cool to see the dampening effect. Okay. All right. So just to warn you, normally if people have talked about the early part of calculus, they talk about. Section 2.4, and I'm surprised if people don't talk about some teachers do it and some teachers don't. I am a teacher that does it, because if I don't do it, it'll screw those of you over that want to actually go further in mathematics, so I don't understand why some don't. 2.4, we're going to do our little tour here in a second, but 2.4 is a proof section, a true, your possibly first real proof in mathematics. So, something to look forward to. So what we're going to do for this little tour, just kind of gather right here for a second. Let me get in front of you guys. We're going to go into the tech mall. That was actually really cool. Oh. Cool, man.
Can we get our pre-test things back?
Oh, yeah.
Which name falls on it? Joshua?
I emailed you. I'm Jeffrey. Kind of come in a second.
Oh, yeah. Here. Do you have a pen?
Yeah.
Did you already take attendance?
No, I didn't do attendance.
Can I turn it over?
Yeah, sure. Thanks, man. Here's a copy of that if you want.
Okay.
I gave away all my syllabi, but did I?
Yeah, you gave
I sent you the. Okay.
I have a question.
Oh, that's right. Yeah.
What is the E30 in every other?
Right up there. Every third minute. Oh yeah, that works. Yeah, that works. I love it.
I was just wondering, on the graphic calculator, how did you get it to...
Oh, if you want, that's the pretest.
I got one of those too.
Oh, you did?
Yes.
Did you just change the width of the window? To
Oh
achieve
yeah,
that?
no, I just changed the output. I made the Y min and Y max 100 and negative 100,
Oh.
just so I can see I can fit it in there better.
Right.
Are you still in the same office?
Oh yeah, so you've gone through it before. So I don't mind if I lose you. That's fine.